be achievable with your device if you ignore the effects of Einstein's special relativity theory? How large do you think is the influence of the magnet in the system? Should there not have been a reference experiment to prove this? Also, did you consider or experiment with many magnets instead of one? Also, considering the size and the mass of the ball or the magnet could have been improved your report. First of all, my first question is, did you ever consider fixing the magnet? And what would have happened in this case?
I did not fix the magnet because in usual Gaussian canon, the magnet is not fixed. And in case of when I fix the magnet, then it is very hard to predict the ejection velocity because the momentum is not conserved through the system because there is external force acting on it. Yeah, and also fixing differs in amount. And if we fix the magnet totally fixed to the rail, then the momentum will not be transferred to the last ball. But since it differs with the amount of fix, how much we...
So you are saying then part of the momentum will be transferred to the rail as well, if you fix the magnet?
Yeah, a lot, if we fix...
If you fix the magnet.
Yeah.
Also, could you present your slide about the experimental velocity and the theoretical velocity?
So, in my research, what I did is my theory predicted the ejection speed very well with low percent errors, and I think it does not mean the theory being less than the experiment is just because that the errors in evaluating magnetic force or other sources of errors, but since, as you see, the error is very small, and I don't think that...
Yes, I understand, but
yeah.
My question is, why is the experimental velocity higher than the theoretical velocity? Do you have an explanation for that?
So there will be some errors in magnetic force measurements, and also during the collision, I may have overestimated the loss of energy.
Okay,
yeah,
that's very good. As the ball approaches the magnet, do you think the energy will be conserved as it approaches the magnet? Do you think some of the magnetic potential energy, the initial velocity, and the initial kinetic energy, do you think will be conserved right before it hits the magnet?
So you mean the first phase, the attraction phase,
yes.
Right? And as I explained before, when you think about this system, then there is no external force except the friction. And about the friction. So the effect of friction is very negligible, so that the energy will be conserved. So here, as you see, the energy loss by friction is 0.001 joule, which is 1/80 of the magnetic potential energy gained by the magnet.
I understand. So you assumed that magnetic force was a conservative force. You assumed.
Yeah.
Okay. I think it might have been much better if you had directly observed if the ball rotated, for example, with a high-speed camera, and maybe it would have aided your experiment. It would have aided your theory, whether you could cancel the kinetic rotational energy or not.
So this is a video I took with high-speed camera with 1,000 frames per second, and as you can see, the screen is dim, but the rotational energy does not reach. So it is perfectly lost by the friction between the magnet, and you can see that before it attached, the first ball slides because of the magnetic force.
So you did not actually measure if the initial rotational energy is perfectly equal to the ejecting rotational energy.
I don't mean that there is no ejection rotational energy.
So there is no ejection rotational energy. So can I see your slide with theory when you cancel the rotational energies on both sides? Sure. I don't understand how you can just cancel that if there was no ejecting rotational energy. And both, I believe, were not equal. May I move on to the next? question?
No, I'm just explaining. So this is just attraction phase. It is before collision. So yeah, it's attraction phase, and I analyze the ejection phase later. Okay.
So did you ever consider the effects of eddy currents?
Eddy currents.
Yes. Could you explain how eddy currents would affect your system?
So when the steel ball approaches the magnet, the magnetic flux through the ball would change and it will make eddy currents. But in my theory, I assume that the effect of eddy currents is very small. And as you can see in this data, so resistivity of steel is much bigger than that of copper, and it is about 50% larger than it. And so, even though the eddy current appears to the steel ball, its intensity will be very small. And so, this is the reason why I assume that there is negligible eddy current effect.
So, if the eddy current was negligible,
Yeah.
it would have been a certain amount, and in your theory, you did not calculate that. And still, in your experiments, the ejecting velocity came out as higher, even though you did not concern the energy loss because of the eddy current in your theory.
Well, I don't think that your argument is that because my theoretical prediction is lower than the experimental value, the eddy current might have effect. But theoretical value lower than the experiment does not mean anything, but maybe I have overestimated the collision, and as I said, the eddy current effect is negligible in my experiment.
Well, may I ask what was the material of the railing in your
It was
experiment? Can I see
plastic.
your picture of the railing?
It's plastic.
Oh, it was plastic. Okay. I'd like to ask you, how did you find the magnetic potential in the force you got measured?
So, what I measured is the magnetic force between the ball and magnet with initial separation. So, I could get the force distance graph, and from the integration, I can get the potential energy.
So you integrated with a computer program?
No, with my hand.
With your hand?
Yeah.
Because it wasn't in your graph, you could just do it with your hand.
In this case, the graph is well fitted.
Okay.
So, yeah. Okay.
I would also like to question the part where you measured the force.
Force.
Yeah, in the picture. If you actually pull the thin film,
Yeah.
do you not think that the magnet will move with the ball in front of the film? And don't you think that will have an effect in measuring your force?
So I will explain my experiment in detail. So as you see here, there is an acrylic ring between the ball and magnet. So if you pull them, this ring is attached to the steel ball so that it gives initial push. And what I measured is the maximum force.
Maximum force.
So I separated the ball from the magnet with slow acceleration, and the maximum force implies the attraction force between the ball and magnet.
Okay, but I want to question if the magnet behind the thin film was not attracted with the steel ball in front of the thin film. Did that not have an effect?
Excuse me?
So if you pull that string,
Yeah.
did the steel ball on the right side and on the left side, the tail film, just come like that?
Come with it. So there is an acrylic ring, and its diameter is bigger than that of thin film. So that here in the experiment, the acrylic ring is perfectly attached to the left steel ball as it is separated. So it doesn't move.
Okay. I would just like to ask your opinion. Do you think an infinite velocity is reachable?
So I have not concerned about it because its Gaussian cannon problem is about initial slow velocity. But as you can see in my graph, the kinetic energy increased because of the magnetic potential energy difference. But it may change because if the velocity is too big, then also the energy loss from collision should be also big. And so I'm not sure about this answer.
Okay. So how large do you think the influence of the magnet is in this system?
So the magnet is what gives the kinetic energy gain. And so what do you specifically mean by this?
So what kind of experiment could you have conducted in order to find how much influence is a magnet? What would have happened if you did not use a magnet?
So if I did not use magnets, then I could use just collision phase in my theory to predict the ejection speed. And I think in this experiment, the magnets real field distribution or real properties of magnet is not important. And the real important thing is to predict the ejection velocity, as I did in my theory.
Okay. This is an additional question.
Yeah.
Why did you consider the greatest effect as the greatest ejecting kinetic energy, not the velocity or the momentum of the ejecting ball?
So in this case, the Gaussian cannon is very different from other toys because even though initial velocity was very slow, the ejection velocity is very big. So this is what is unique to this Gaussian cannon. So this change in speed can be represented by change in kinetic energy. So that's the reason why I interpreted the largest effect as kinetic energy gain.
But I thought you mentioned about the greatest ejecting velocity. Why the kinetic energy?
So
could you have varied the mass of the ball if you wanted the greatest kinetic energy?
Sure.
So I want to emphasize that from my theory, I can predict the ejection velocity, and from that ejection velocity, I can get the values of momentum, kinetic energy, and every other values.
That is only if the mass is the same.
Time's up for the discussion. So I ask the opponent to summarize the discussion in a minute.
To summarize this discussion we have just had, the opponent did not consider the fixing of the magnet because he thought that it would have an effect on the influence the momentum of the rail as well. And he thought that he did not explain why the experimental velocity was always higher than the theoretical velocity, and except of saying that they might have some mismeasurements in his measuring of force. Also, he did not clarify on the fact that magnetic force was a conservative force or not. He might have done better if he mentioned that part. One of the fundamental things that I saw in his report was that he neglected the influence of rotational energy greatly. He did not check the rotational energy of the ejecting ball was the same as the initial attracting phase. Also, he did not. Yes, he used the right railing with plastic. Yes, thank you.
Okay. I'd like to thank both teams for a wonderful discussion. And the reviewer, please feel free to ask questions to both the opponent and the reporter.
First, I would like to thank the reporter team for your great presentation and the opponent for your great debate. For the reporter, I would first like to ask, I would like to show us the energy equation that you set up. Yes. What can you explain the variables in the equations?
So here I assumed that the initial velocity of the first ball is v0, and right before the collision is v1 and v2.
I'm sorry. Can you exactly define what the EDC is?
So this is decrease in magnetic potential energy because the ball attached to the magnet has more magnetic energy than separated from them.
Do you have a quantitative model of your calculation of magnetic potential energy?
So I did my experiment, so I measured the magnetic force versus distance, and by integration I could calculate the magnetic potential energy.
Also, what happens to the rotational energy of the first ball?
So In fact, the rotational energy of the first ball does not transfer to the last ball at all. It is just lost through the friction between ball and magnet, or ball and the rail.
Also, what is the loss ratio due to the collision simulation that you have set up?
Loss
Ratio. The ratio of the energy loss.
Energy loss. So there is no specific thing like ratio in energy. You mean just ratio of energy loss. And I approximate this like 75%. Yes.
75%?
The energy is 0.08 joule and it became 0.06 joule.
Okay. And can you explain more about under what conditions the ball at the opposite side of the magnet, more than one ball is ejected? You said that 2 balls were rejected.
So, simulation. So in my simulation, I could also predict the energy dispersion here. And so the balls are actually folded with the magnets.
Other than quantitative explanation, I would like some more qualitative explanation about under what condition more than 2 balls are ejected.
So after the collision, the other balls also gain velocity, and if the velocity is enough to overcome the magnetic attraction, then the other balls will also be separated.
Okay, thank you. The reviewer, please take a couple moments to prepare. Okay, a reviewer, you have the floor. Please start the time.
Thank you, the reporter and the opponent team, for your fierce yet a very fruitful debate. And thank you, your honorable judges, for your time and attention. This is Yoon Lee from Hanyang Foreign Language School, and I'm here to review on the question number 1, the Gaussian canon. So the problem is stated as this. And the keywords defined were identical steel balls, strong magnet, non-magnetic channel, and the word collision. And the objective was to optimize the magnet's position for the greatest effect. So, to summarize the report's presentation, he used theories of momentum and energy conservation and energy loss and dispersion to explain the model, and he divided the phases into 3, attraction, collision, and ejection. And he set the parameter as a number of balls in front and behind the magnet, and for the experiment he used inclination and Forgate to record the ejecting and the initial speed. And his conclusion were that the 3 and 4 balls behind the magnet were the most appropriate. And there were some strong points and weak points of the reporter. First, he had a good flow of presentation, and second, he had a good interpretation of the problem. It was nice to see that he divided the process into 3 phases and explained thoroughly. And lastly, he had a good explanation with simple theories that we could easily follow, such as the energy and the momentum conservation laws. However, he had some weak points. First, he had weak definition of keywords. What magnet did he use for the strong magnet, and how exactly did he define the position of the magnet? And second, he lacked parameters. He had only one parameter, the number of balls front and behind the magnet. And third, he did not take the dipole and dipole interaction into consideration. And so it should have been better if he took other sources of energy losses into consideration. And for the opponent, he had 2 strong points. First, he was able to point out the critical errors in the reporter's presentation about the unclear explanation about the theories and the flaws in the theories about the eddy currents and the dipole-dipole interaction, and the difference between the theoretical and the experimental values. And he made efforts to clarify on the weak explanation. However, he had 2 weak points. First, he missed out to point out the essence of the problem. What is the position of the magnet? And what is the theoretical error in the reporter's presentation? And also he missed to point out under which condition did the more than 2 balls were being ejected. And the overview of debate was that opponent asked whether he considered fixing the magnet, and the reporter asked that the momentum is not conserved when fixed, and it differed each time.